And now I just want to demonstrate how I reconstruct a block and then figure out, based on context, what any missing bytes are for errors like that. So let's have a look at reconstructing a block. This is actually one of my Mighty Frame tapes. I am reconstructing track 1 for CTIX 5.11 16 user. And I found an error in block sequential number 13918, and that is that's on track 1 of this particular tape. It's software installed tape, CTIX 5.11 16 user. You should be able to see a picture of that tape somewhere else on my site at mightyframe.com. Now, let's have a look at how it is that I handle this. So I've created a few other videos for block reconstruction, I think. I've kind of lost track because I've created so many. But I'm going to just assume that I have, and kind of pick up where I left off, where I think I left off there. Hopefully it'll make sense. The programs that I write identify a bad block, and they insert this for me so that I can easily find it. I'm going to go to one of the key reports here. It's the data block bytes report. I don't know why I named it like that. I have difficulty saying it. It's a tongue twister, but I did. The data block bytes report, the CRC verified version. And when I come across this, how do I come across this? I just search for these characters right here, a string of these. I rarely find 5 pipes in a row anywhere. I've never seen that actually in software, or very often in data. It's kind of something that I like to do that's unique to, as a kind of a marker for my own notes. So I'm searching for the marker for my own notes, and it's usually 5 pipes in a row or so. And so I just simply go through this entire block read, most of which I've cleansed and reconstructed by now, but I'm just going through this entire block read, which is, if there's multiple files spanning the track, those are separated by my file mark block notation right here. I'll later manually separate these into separate files using this hex editor, but I'll step through all those until I find some block errors. Block sequential 13387. Now, that is sequential block number in the track, not the block number as identified by the QIC24 format. I'll get to that in a moment. I just wanted to make that distinction. Now, I'm going to skip over this one because this one was a little bit too complicated, and I didn't have a good solution for it. Most of them I do have a good solution for, and what I'm about to show you is something that works. So we're going to do a block repair, block reconstruction based on context on block 13918. Actually, it's going to be block 13919. I'm sorry for the confusion there. I did a reread for all this and made some improvements to my programs, found some missing blocks. So I'm going to use just block 13919. Okay, that's what I'm wanting to reconstruct. Hopefully it's not going to be too confusing. I'm going to insert that here when I'm done. I just happen to know that this is the version that I was using, and block 13919 in this version is the same as block 13918 on this version. Okay, hopefully that's not too confusing, but let's move on. The most important report is the data block bytes report, CRC verified version. So what I'll do is I'll look for this block here, and I even have the timestamp. That's always helpful to find the whole thing. And I've already done that, but I'll just do a Control F, find, and it finds it right there. Usually I start at the beginning, Control F, find, it searches for a moment because it's a long file, and it finds that. I'm opening this in Notepad right now, and I have word wrap off. That makes things run a lot smoother. Now, what I like to do particularly with this QIC24 format that I'm working with today, is I like to copy 2 blocks ahead of the problem block and 2 blocks after. And I just copy those into another file that I work with. Makes it a little bit easier to work with, which I've done right over here. I've just created a new file for the blocks that I'm repairing, and I'm going to run a separate CRC check on that. Okay, so I've already copied that over here. And I'll do it again, because I want to demonstrate how I do this from start to finish. All right, there we go. Now, I'm going to close this to get it out of the way, because I've copied the relevant information over here. Now, until I improve some things in my program, I'm going to do some things to strip the calculated CRC, because what I'm doing is I'm turning this into a pre-CRC calculated file that I'll run the calculation on again once I reconstruct the block, just to verify that I've done it correctly. And here I like to edit replace this, the written, because my CRC verification program inserts this written right here. It inserts this. So we're going to replace those with nothing. There we go. They're all gone. So now this is very nearly exactly what you see in the data block bytes report prior to the CRC verification program that I have. So I'm going to save this. Okay, now, usually in this case we have an error where there's a dropout or some missing magnetic flux transition, some missing data pulses, somewhere in the middle of the block. It works out really nice when there's just one, and we found errors. In this particular case, we found a number of warnings, a number of errors. I'll make this full screen here so we can see it a little bit better. Okay, so there's no postamble found, which is denoted by the sequential P's by my program. See how these have sequential P's that says, hey, I found a postamble. So the first problem my program identifies is that that's not there. And then it identifies more problems, that it contains, the data block contains unrecognizable hexadecimal characters at 925 nibbles into the nibble count. And then, a third problem, the data block contains too few nibbles. It's not long enough. So what I'm guessing here is there was a complete dropout in data pulses, and the block was ended by my program because it's designed to do that when it finds a gap that's just too long. That keeps it from accidentally running over into the next block. And so we'll just have a look at that. Now right here, I see that X right there? My program's put that in when the gap is too long. And I think I'm going to do a visual here because I want you to see what this looks like. We're going to go to 82.0319. 82.0319. Am I in the right place here? We'll open this file. Right here. This will be fun. Oh, I didn't copy that file over. All right, let me open the right file in the right place. Okay. My source file I just happen to have over here. Please don't be confused by this. Close this while this opens. All right. So this should be the correct file I'm working with. This is the no, wrong file. Ay. 1R, 2 turns down is where I am. That's where I am. This should be the correct file. And I think it is. Alright, track 1R, 2 turns down. Is that what I'm working with here? Track 1R, 2 turns down. Yes, that is what I'm working with here. That's the file I'm working with. Okay, so where am I going to go? I'm going to go to 82.0319 so that we can see exactly what this problem was. Didn't need to do that. 82.0319. So 60, 70, nearly 80, because the entire read for the entire track was only 85 seconds. So very near the end of this track. 82. All right, so that's 80, 81, 82.0. 82.03190. 82.03. All right, so that would be 0.1.031. I can see it right there. See that? It just opened right up. Yep, 190. 82.03190. 191. We're in the general area. But here's the thing. You see this nice, healthy data pulse spacing, and then all of a sudden we run into these wide gaps. Well, there's a physical problem with the tape there, I'm imagining, that actually affected multiple tracks. So wherever the block happened to line up on other tracks, we had a very, very similar problem. So there's a flaw in the tape, some degradation on the tape, but it only affects this amount right here. So it affects from here to about here. I think I'll move this. Yeah, it affects from about here to about here. Yeah, there we go. It affects that area right there. So there's a number of data pulses missing, and I'm not exactly sure how many bytes this represents yet. I don't think it's too many, thankfully. So we're going to have a look at what that looks like. Maybe that's, only 2 to 4 bytes. I think that's all that would be the case there. 2 to 4 bytes is what I'm going to guess. Okay, so what I do, my data repair project, is I take all of the data from before. Oh, whoa. There we go. So all of the data from before. So here's the postamble preamble. The preamble for this block, that's the data block marker. The block starts here. Everything's going along just fine until we see this dropout. Let me squeeze in a little bit here. Yep, everything's going along just fine. We can move back just so you see it again. All right, so there's the preamble postamble at this zoom level. Everything's going along just fine for a good part of the block, and then there's this dropout, and then the data picks back up again until we get to the postamble. Now, this is very typical of these errors. So what I do is I already have the hexadecimal characters for right up until the dropout. But then I run a special block repair program that does a bitwise shift of 5, so that it gets all of the 5. It calculates all the 5 combinations, basically for this section right here. And based on that, I can see which one I want to use, which one would be the most valid one. Let me show you exactly what that looks like. So here's what that procedure looks like. There we go. Okay, so here in this case, we see that everything's going along just fine. 700491X. And because X was just too long of a data pulse, and I would imagine just visually, that would probably be either this one or this one. One of these two is just way too long. Either way, it just ends. It just says, something's wrong. As a matter of fact, I think we can even find that part in the well, let me show you. I actually have a data bytes block report, an error report. It's not where I want to be. Let's go to, here we go. That's where I want to be. Okay, so if I were to look for my bad block report, what block am I working on right now? I'm working on block 13919, sequential block 13919. And so when I go to that, I want to find that one, 13919. I have this nice report. And this report basically shows me the timing of every single nibble here. So we had a dropout what I'm going to do, I'm going to go to block 3919. There we go. That's where it dropped out. So here, that's not a good example. I'm not going to use this as an example. I'm actually going to go to the master decode log for that set of 10. Is it 10 or 20? It's 20 blocks. 13919 is what I'm looking for. So I'm going to see 13901 to 13921. So 13919 would be at the end of this file. Let's open this one up and have a quick look. Let's look at where block 13919 ended, and we'll see it right here. All right, this is better. So basically, right here, it ends, and it finds that this is too long of a gap, that's too long of a gap, that's too long of a gap, that's too long of a gap. 4 of them in a row that are just too long of a gap. And I would imagine that that is 1, 2, 3, 4. And then it finds some things that look like they could be zeros and ones because they're narrow enough, they're within the range. And so it identifies those. It identifies the 100 at 3 microseconds. And it identifies the 1 at 1.5 microseconds. So that's the one at 3. And that's the one at 1.5. I just wanted you to get your bearings there so that you could understand what was going on. And then this, of course, is too wide again, so that's another X. X, 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 X. All of these are too wide, right? So this is useless. This is the useless area because anything in here is pretty much meaningless because it's completely out of context. It doesn't come back again into context until we get a steady stream of data pulses that are readable. So we're just going to discard this entire section here, but the magic is we're going to figure out what it was using contextual information. Okay. So this is the bad area. We're probably going to pick it up right again right here. Now, I have a program that does this. It reads this file, it looks for those things, it does all that stuff for us. And it's kind of clumsy, and I'm rewriting it so that it's not nearly as clumsy. But basically it gives me something that looks like this. Here we go. These are the shifts. I think I've had another video that demonstrates this a little bit. Now, this is the end part, and I already have the beginning part. So let's close this. I've showed you what I think I needed to here, out of the master decode log. And so let's look at the beginning and the end. All right, so here is, I'll reverse these so that it's a little more left and right logical. So on the left here, we have the beginning. This is the beginning of the block, right here. Sequential block number 13919. The previous block, sequential number 13918, was just fine. Notice that the QIC 24 block number identification was block number 27,787. That's going to be important, so remember that. We couldn't get a good read on this because, the data block address and the CRC weren't there because the block ended prematurely. That's okay. We're going to get it back using this process. So what I like to do is I like to look here just kind of manually, and I look for the first invalid character, hexadecimal character, and that happens to be that X right there. So I'm going to take this and I'm going to copy it and I'm going to paste it into a new file here in my HXD hex editor. There it is. So, magic, there's the first part of the block. And this is where it drops off. Now, there's some question as to whether this byte is correct. It probably isn't. It's probably incomplete. So I should assume that it's bad. I'm going to leave it there just for fun. Just for fun. And I'm going to add my notation. See how I use this sequential pipe? I just like to do that. It's just something I like to do. Just to say, hey, this is the missing area. Okay, So now we're going to go over to the result of my other program, which does block repair. And basically, it identifies the section out of my master decode log. And it puts it all together, and it does a bitwise shift. And it gives me 5 different examples, because there's 5 possible different positions that it could be in. And it's difficult for me to articulate, so forgive me, but I'm going to show you what I mean. So I just turned on word wrap here, which isn't too detrimental, because it's not that huge of a file. Here's all the binary. My report just gives me the whole thing again. This is not the binary that we can translate into hexadecimal, but this is the GCR 45 binary. So for every 5 digits, it's a 4-bit nibble. 10010. That's a nibble. That translates into 4 binary zeros and ones. 11001. You have to understand GCR 45, and hopefully my site has explained that extensively. Maybe I'll go into that later if anyone is interested. Okay, but the key of what this does here is this goes through all of this and comes up with hexadecimal values, but it shifts it. It looks at everything in sets of 1, 2, 3, 4, 5, and it says that's where we want to start. Then the next set starts here, 1, 2, 3, 4, 5, and it translates 00101. The next one starts right here, and it translates 01011. The next one, like this, 10110. And it does this across the whole thing. It takes a few seconds at the most. It's not so bad. But it basically gives me an output of this. And it's usually incredibly obvious which one I should use. Now, remember, I have the beginning, so I don't need that. See here where the beginning looks nice? Those are all valid hexadecimal characters right here. I don't need that. I already have that right here. We're looking at it. You saw where I got it from. What we need is the end. So we're going to look for the end. So that's the reason that I turned the word wrap on, is because it makes the end a little bit easier to see. So here's the end right here. The key is, if I see a valid set on the end, that's always going to be the one. So that's not valid. Look at all those X's. This one certainly could be valid. I don't see any X's or other bad characters, other bad hexadecimal characters. That's got X's, that's bad. That has X's, that's bad. And this has X's, that's bad. So I'm going to say it's this one. This particular shift has revealed the correct values for the end, the last half of the block, after the bad spot. So what I'm going to do is I'm just going to go up here and look for where the bad spots begin. So what I like to do is I just put the cursor right there. I'll do an edit, not a replace. Just leave the cursor right there. I'll do an edit find. And I'm going to search up instead of down. And I'm just going to search for an X, because that's the most common thing that my program finds when there's a problem. Look at that. It found some things all the way up here, but we have some M's and some other things. And also, let me point out, I'm opening the wrong file. Forgive me. I've worked with a couple of different ones of these, so forgive me for opening the wrong file. Okay. Here's the file I want to use. That's good, we get more practice. Block 13919. Repair, shift decisions regardless of X's. That's what I called it. That's what we'll go with. Okay, so here we are. And again, I'm going to look at the end of these, and I'm looking for things that are valid. Well, we got a bunch of X's right there. No. We have a bunch of X's right there. That's not so good. This one looks pretty good. I don't see any X's, M's, or S's there. By the way, M is file mark, S is sync, R is reverse sync. So those are all not valid hexadecimal numbers, but they are valid for certain formats, GCR 45 groupings of 5 bits. They are valid for other purposes, just not for hexadecimal to go into the binary file. Okay, so this looks pretty good. Before I look at this too deeply, let me look at the rest of them and rule them out. A bunch of X's there, that's not good. And a bunch of X's there, that's not good. So it's pretty obvious this is the one that I want. So let's try that again. where I leave the cursor there, go Edit, and find Next, and I'm going to go up and look for the X. And there it is right there. So I have X9, so I'll just put a few return characters there. This should be the end of the block now. So let's put this back together and see if we can splice it together manually and make sense out of it. All right. So what I'm going to do is I'm going to paste this here. Now I have to be very careful. When I work with the end, I have to make sure that I start with an even number of nibbles. Now I didn't count that, but this is going to become very, very obvious. I'm going to show you how I look at that. I'm going to paste here, and I'm going to make sure that we have the right number of nibbles. Now, I suspect I didn't do this right because of the way this looks. Let me show you what I mean. That ended with 91F3. Those are the last 2 bytes of this, 91F3. We'll look at what I pasted in. This is a nibble shift. C91F30. It assumed, the hexadecimal editor just assumed that because I didn't put something there, it just inserted a 0. I don't like that. Maybe that's a setting I could change. But it was pretty obvious. If I knew what to look for, it became very obvious that I had done that wrong. So this is a very simple fix. I'll simply undo what I just pasted there. I can use Edit Undo. And I'm going to just choose one less. So instead of starting with the 9, I'm just going to start with the 8. Just drop one off, because the way that was, it was X9. Right? X9. Well, that can't be right. So the first possible valid byte is going to be 82. Hexadecimal 82. So let me copy that, paste that in there. There we go. So 91F3 is what I'm looking for at the end, and 91F3, yes, that's correct. So that's what I have. Good. Okay, so I've pasted the back end of this block in here. Now, here's what else I know about QIC24 and QIC11, incidentally. All of the data block the data block sections are 512 bytes exactly. So we're a little bit more than 512 bytes exactly. Now, the data portion is 512 bytes, but then we have the block address and the CRC. So I happen to know exactly how long that is. Here is the block address right there, and here is the CRC. These are known lengths, which means that the last byte in the block, the 512 byte data block, is this. It's the FF. The last 2 bytes are 56FF. Okay, so, and this also makes sense if you dig a little bit deeper. I am looking for a 1 here because we're on track 1, and the first byte in the block address would be the track number. There is the track number, and here is the block number across the entire tape. Excuse me, right here, 006C8C. That's the block number across the entire tape. So track number 1, block number whatever that is. We're going to find out in a second. And then 91F3 is the CRC. So here's what I want. I want this section to be the only section of what I have here that's going to be longer than 512 bytes. I want it to be this much longer than 512. Now it becomes very easy. So now I just go up here, and now I'm just going to start deleting these pipes until I get to the right number of bytes right here in this repair file. Okay, so we're getting close. Basically, I want this 01 to be right here in this position, the 513th byte. And it'll be there in a minute. 1, 2, 3, 4. There it is. Okay, so we're now reconstructing this block, and it's looking pretty good. So now we can see pretty much exactly what we're missing. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. I was off a little bit. We are missing 17 bytes here. And let's assume that this one is highly likely to be not accurate, and this one is highly likely to be not accurate. Okay. Now, that's a chunk. It's not huge, but unless you figure it out, and if this is a very important part of the program that's on this file, on this tape, then, you kind of need to figure out what that is. Well, as luck would have it, there's enough other examples of whatever code this is that I could pull this from. So let me show you what I mean by this. We're going to say that we want this this is what we're going to replace here. 1 byte before and 1 byte after the missing section. That's what we want to replace. So now that I've gotten this far, what I like to do is to look at basically all of the bytes in other similar tapes and see if I find a matching pattern. And if I do, then I should be able to fill in the difference. And then I don't have to guess and assume that I got right, because I can verify it with 100% accuracy by checking it against this CRC. The CRC calculation against what I put in here ends up matching the this CRC right here that was originally written when the tape was written by the hardware, the tape hardware. Then we know that I got it right. So we're going to go all the way through that, and I'm going to show you exactly how I did that. Now, this is a CTIX version 5.11 install tape. I just happen to have already restored, successfully, I might add, another version, CTIX 5.25.1. And what I've done is I've taken all, I believe it's 43 files on that tape, which I've used, by the way. I've used all 43 files on a QIC tape, and I've actually done a new build on a Mighty Frame with that. I'll show you where that is. We'll go to mightyframe.com, which is my site for several of these projects. Just search for this. There we go. Install tape restored and used. So what I'm showing you is the files that I restored from this particular tape. Now this tape, I didn't have to use my universal QIC reader. I was really, really lucky, and I was able to use standard QIC 24 reading hardware, which just happened to be my Tandberg TDC 3620 with the SCSI adapter on a modern Linux machine. It worked very, very well. If you want to read more about how I did that, just read here. But that only works if there's not errors with the tape. We found errors with the tape, the Universal QIC reader, we're going to fix them now. But because I have this, I have context. And so, here's the context. Here's what I'm going to do. Here's the magic. Now, this doesn't always work, but I like to get lucky when I do. All right, so I'm going to assume this byte's bad, maybe this one too. I'm going to assume this byte's bad, maybe this one's too. Not so sure. So I'm going to start a couple bytes before this, and I'm just going to take a section. Maybe, I don't know, 32, 64 bytes. A nice section that wouldn't occur randomly, or wouldn't occur elsewhere in the file unless it was meaningful. That's kind of a subjective thing, but with this vintage of software and stuff, I'm actually finding that this is working pretty well. So bear with me here. So I'm going to copy the hexadecimal characters for this, and I'm going to go over to this. And this is all 34 files on the tape that did work. This tape, different tape. All 34 files concatenated. I actually used the Linux cat function to just put them all together. And its only purpose is so I can see all the bytes from the all 34 files in the tape, all in one place in my hex editor. So what I'm going to do is I'm going to do a Control F, and I'm going to search for hex values. And I'm going to paste those hex values. I've selected hex values, and I'm going to say search direction, all. Search the whole thing. See if you find a match. Click OK. Look at this! I found one match! Okay, that's probably not a coincidence. That's probably because whatever is in this file might, be repeated in a few places. I don't know why that is, but in this case, it really is. And it's not repeated just one place, two places. It's repeated in 2 places. Now, let's see, what I like to do is to say if I see a correlation where this has the same sequence of bytes before and the same sequence of bytes after the missing section, and then the same number of bytes right between them, chances are pretty strong that that's what I'm missing. So, I found this section right here, right? I found this. Let me drag this over so it's a little bit easier to see. Found this right here in 2 places. So I'm going to just work with the top one. Yeah, I'll work with the bottom one. It may not matter, because they really may be both examples of exactly what I need. So here's what I want to see. Here, I'm going to start with, let's say, this section right here, which is 2 bytes after the bad place. So, again, I have to, with this hex editor, I have to select this, otherwise I select the text characters. I don't want the text characters, I actually want the hexadecimal values, because that's what I'm searching. So now, if I do a Control F, and I search for those hexadecimal values, ideally, it wouldn't jump somewhere else, it would jump just a couple lines below here in my reader. So let's see if it does it. I find that in 2 places. It repositioned, so I'm not exactly sure what I found. Did it find it? Let's go to the previous one. Is it right above this? Yes. See that? It was right above there. I don't know why it repositioned the screen. It kind of faked me out. But it is. So what I found is a good chunk of bytes before, hexadecimal characters, whatever you want to call it, a good chunk before the bad spot and a good chunk after the bad spot. Now let's see if the whole thing is really what I'm missing. And I'll bet it is. I'm just going to take a chunk. That's more than what I'm missing. And let's actually create another file here like this. Okay. And what I'd like to do is now take out this chunk right here. Just like that. See if I can get a match. I'm going through a little bit more trouble than I usually do, but I really want to demonstrate this. Okay, so now I'm just looking at these characters. Now these don't mean anything. This isn't text for people to read. This is, values that this computer will read. So this is some compiled, I think it's a compiled C program, actually. Because there's a lot of compiled C programs on the Mighty Frame, particularly with the install tape. But I'm just going to look for this. .RA, degrees, .GRE. This is just a mental exercise, what I'm doing here. So I'm just kind of finding the match here to coordinate this up. .ROGRU. And I can even do this. We can even take the search a little bit further. Again, I'm going through extra value here. Oh, good. Good, okay. So, it looks like, there we go. Look at that. I've now lined up the difference. And look, let me get rid of this so it's real clear to see. Here's the bad section. Look, keep your eye right here. Here's the bad section. I'm going to click over here. Look at that. And keep your eye here as well. Notice how this doesn't change from here to here. The bottom line and the hex editor, see that doesn't change? We've already found a match using a search, so we know it's the same characters. It's not just visually fooling me, it is. So, and it's not shifting, which means I've actually found the hexadecimal characters that I think I'm missing. And now we're going to prove it. Because we don't have to guess and say, gee, I hope that's right. We're going to prove it. So, I'm going to just do a match here. And I'm just looking for things that my brain can recognize. 0NV, yup. Whatever that is. And then EYEN. So, 0NV, yup, before, and EYEN after. So what I'm going to do now is I'm going to go back over here. Find that same thing here, right there. So this is the section that I want to grab from the file, right? 0NV, yup. All right, so here, 0NV, yup, to EYEN. How did I do that? Let me get it right. Let's just go to EYEN, like I was saying. Right there. A little bit more than 32 bytes. Segment there. And here is the same segment right here. And again, I have to copy on the hexadecimal side, not the text side. Notice this is darker than this. That's just how HXD works. But it's a nice feature. I like it. Okay, so I'm ready now to replace this with this. So I'm going to copy here. I'm going to go over here and I'm going to paste. Boom. There it is. Now, I believe this is the block, the complete block. How are we going to prove it? We're going to run the CRC check against it. And if it's a match, the CRC matches, then we know for certain, 100% certain, that I got this right. So, now that I've done that, I'm just going to copy these right here, and I'm going to put them back into something that my own programs can recognize. Now, HXD likes to put these spaces in. I'm just going to quickly remove those, edit, replace, space with nothing. There we go. And I'll copy this. This now is the exact block that my data block bytes report likes to have. So I'm going to manually insert that right over here. Yes, that's what I want, right here. So I'm actually going to close this. I'm done with it. That's already in the clipboard. And so right here, I do not have word wrap on, but I'll go, that's okay. I'll go full screen here. Now remember, this now I can discard. So I'm going to get rid of it, and I'm going to paste. There it is. Paste that in. Now, this is all lining up so far. Notice this is a good block. We're right up to the P's. The P's are the preamble, postamble. Notice how that comes to right here, lines up right there. So we have the right amount of hexadecimal nibbles here, the right amount of hexadecimal characters. I'm going to copy and paste. Now I'm going to manually fix this so that I can run my CRC check on it, and it can read this as input data and give me output data. So, the CRC I already know. I'm going to do some things that aren't going to make sense. They're just going to match what I did with my program. 91F3 is going to be the CRC. Now, the computer doesn't care the decimal value of that, but because I do text line comparison, all these others, for some strange reason, just because I wanted to know, I just decided to display the decimal. So I'm going to make sure that this matches, because that's what my program is going to verify, is that this line is an exact match. So I'm just going to go to a hexadecimal converter here online. They're all over the place. 91F3, click convert. There's the decimal value. Again, that doesn't mean anything except I'm just making my own file complete for my own program. Okay? Now, the track number, again, because I know the anatomy of the QIC24 data block, I know that 01 is the track number, and I know that 006C8C is going to be the block number. So I'm going to paste that in there, and in this case, I'm going to translate that into decimal, and you're going to see that's actually going to be very helpful. So here we go. Convert. That goes to 27788. Very good. And I'm going to paste that right here. Now, look at this. Already, I can see that things are going well. That I've at least, I've gotten the back half of the right block accurately, because the data block number on QIC24 format, every single block on the entire tape is a unique number. It goes from 0 to however many tens or even hundreds of thousands of blocks are on the tape across all 9 tracks. So here we have block number, and because I don't read hex very, very well in my head yet, I think the decimal is very helpful, because I can read decimal, have been able to since I was quite little. 27786 is this block number. 27787 is this block number. So the bad one should be 27788, and it is. And then the one after it should be 27789, means nothing is missing. And the one after that is 27790. So it fits in the sequence correctly. So now the only thing to do to prove that the process that I just used to reconstruct the missing bytes in this block will be to run my CRC program. And here we go. Let me clean this up again. This alternate block, this was the warning that my program used to insert this right here. This right here, this segment that says, hey, you got a bad block. That's actually the hexadecimal characters for that particular warning. Let me close this. We're done with this. No, I don't want to save. Close this. Done with this. Don't want to save. Leave that open. Where did I go? I got lost. Yes, I wanted to go back to the data block bytes report. So I'm just going to get rid of this because it's not necessary for now. I'm going to go restore this to warnings equal none, which is just what my program would have written had it found no problems with the hexadecimal characters here. And this is what the pre-CRC check data block bytes report should look like. So now that I've manually reconstructed this, I'm going to run my CRC program on it. We're going to prove that this really was what the block was when we get a CRC match. And hit save. And I'm just going to run that particular program. I have a button for it right here. CRC calculator. I think I have to do something funky with the source. Yes, I do. Source files. I'll explain this another time. Okay, run it. 1, 2, 3, took 4 seconds. Great. Now I'm going to go over here, and I'm going to see CRC verified. Let's open it up and see how I did. Alrighty, I'm going to take off word wrap. So let's have a look and see how I did. So, it was the third block in, right? This block was fine. We see the calculated CRC now matches the written CRC. So the program verified this. I already knew it would because my program had already verified that before. Same with this one. Calculated and written are equal. And here's the magic. Uh-oh. Looks like I'm wrong. I should have picked a bad example. After all that, I now proved that this process didn't work. All my other examples it did. I've now proven it didn't. Well, but I think that's good because that keeps me from fooling myself into thinking that I've solved something I haven't really solved. And either I made a mistake somewhere or the sample that I pulled from is not the same as what the block used to be. So I'm going to think about this some and see if I can come up with a solution. But I will tell you, this has worked for other blocks. I did this exact thing, for example, right here. I did this exact thing on this block right here, and it did work. The exact thing that I showed you. And it did find the calculated versus the written to be exactly correct. But at least this is how I know for sure. So I'm glad that it found an error if it was really there. So let me continue and see if I can figure out what it is. And we can still get lucky, so you guys are going to watch me do this live. I don't know if this is going to solve the problem, but it might. So I'm going to do this again. Those files I closed, I shouldn't have closed them. That's okay. Alrighty. Here's what I want, right here. Okay, this is what I want to see. Right here, I'm going to do a new file, and right here at this section, I'm going to go for 3 blocks, 3 sets of 32 bytes. Yep, just the 2. Okay, so I pulled this from the first one, I think, and not the second one. And I'm noticing that there's like 1 hexadecimal character different. Maybe I can still get lucky. Let me show you what I mean by that. So here, 1, 2, 3. There's 3 there. Okay, so there's the bad one. Here's sample 1. Sample 1. And let's do sample 2. Okay. There, that's sample 2. 1, 2, 3. Okay, look at this. Right there, you can't see my finger, but 1 hexadecimal character changes in the midst there in between these 2 examples. So we can still get lucky. We can still get lucky. See this P right here changes to a bracket right there. Now, of course, what we have is the hexadecimal value over here, really. It's 50 in this position. Excuse me, 1350 in this position. And it's 1E28 over here in this position. Now, I know these things are valid because this was a perfect read. All CRCs worked as verified by the hardware, not even my programs. And it's successfully installed without errors on a Mighty frame. So I have all kinds of indication that, you know, these are right for what they are. But see, it's a different version. This is 5.25.1. I'm trying to restore tape for 5.11. It's the only one we know in existence, which is why I'm working so hard at this. So here we go. Let's get lucky. See if we get lucky. I am going to run this exact same thing, just changing those 2 bytes, and see if that makes a difference on a CRC. Now, to do something I haven't done here before, and I am actually going to duplicate the block in my program just to see them side by side. But I can do that because it's my program. So, here is what I did the first time. Set these 2 apart right there in the middle. All right, so now I have a duplicate of block sequential 13919 or block number 27788. 27788, 27788. There we go. That is exactly what it should be. Now, which one is which? Well, I'll use some process of elimination here. Oh, come on. There we go. So, it's that one. And, well, these are both going to be the same because I copied them. All right, so what I want to know is this one E28 or 1350? I just happen to visually see it right there. It's 1350. So I tried 1350. 1350, according to the CRC, is not correct. So, let's try 1E28 there. All right. 1350 is not correct. Let's try 1E28. 1E28, there it is. Okay. So, there's a couple of different ways to do this, but, you know, it's just text manipulation now. Edit, replace, the space with nothing. Okay, copy that. And let's see, I should be able to now go back here. And, nope, that one. The second one. And there it is. So these should be slightly different. And it's just these 2 bytes that are different here. Let's see if I can find them visually in my own report. 1E28. I don't know how many of those are in there. 1E28. I think I found it. Such a subjective process. Yes, 1350 is right there. 1E28 is right there. Otherwise, everything else is the same. 651C201, 651C201. Okay, so we cross our fingers. Chances are this is going to be a CRC mismatch, but this one this one could just be a match. And if so, we have figured out the magic. So, I'm going to save this, and I'm going to run the program one more time. Run the program one more time. This time I'm not going to close these things. Okay. Make sure I don't have it open. I don't have it open. So, let's run the CRC calculator on this. And cross your fingers. CRC verified. Open it up. That was it. That was it. We have an error on this block. CRC mismatch. But here, we really got lucky. That's it. So actually, I think this turned out to be an absolutely fantastic explanation of exactly how I can use bytes from a contextual file and see if we can reconstruct, with a lot of trial and error, but reconstruct what might be missing because there's a dropout in the tape. And I've proven that it's possible. It may not happen all the time. You may have to use some more advanced techniques, but it's possible. Right here. It's possible. That is it. It is a match. CRC algorithm came up with this number. This was what was written by the hardware 30 years ago, or however long it was that these tapes were actually written by the manufacturer at Convergent Technologies. And there we have it. And everything's happening. 2287, 2288, 2289. So this is the one that I'm going to use right here. That's the one. Wow. I'm going to paste that right here because that's the block I'm working on. And it goes right there. And there it is in context. So I have just replaced the bad block. I could do the same over here if I wanted to, except I'm not going to use this as my final version. But there it is in context. So you have now seen how I can actually use contextual data to come up with really, really good guesses about what the bytes are that are missing on a bad block and prove it that I'm either right or wrong and then use it to replace it. So this now is going to make this a very complete file. And I believe that there's only one error left in this entire track. File mark, file mark, file mark, file mark. All those are happy files. There's no bad blocks in them. Okay, this is a bad block I'm still going to work on. I think this one's going to be a little bit more of a problem child, but I'm going to get there because I'm just that persistent. And then that's it. So, unfortunately, it was part of the same file. So this is going to be a problem file. Looks like it's file USR bin 300. I think that's how these file names work on these tapes. So that's the file I'm having the most difficulty with. But I'm going to get it just because I am that determined. And I think when you go to these levels, you can see that it really is possible to, if you're willing to put forth enough effort, to really read some bad tapes and figure out exactly what they were supposed to be. I really think it's possible. So, anyway, thank you very much for watching. I realize this video has gone on now for nearly an hour, but I hope it was interesting and educational for you. And thanks again. Love to hear your feedback. Please leave the comments below on YouTube. Bye-bye.